morning. How are you?
Good morning. Good. How are you doing?
I'm good. It's a good Thursday, huh?
Yeah.
Oh, it's another one of those. I'm not quite ready. My son's been out sick, just with some kind of stomach thing. But in order for him to go back to school, he has to get a COVID test. And so that's what we rushed off to do this morning. And it's just one of those rapid tests, but the school has to do it so that they know that we're not faking the results. But the problem is that they're taking their own sweet time to send in the results, even though we had the test now almost an hour ago. Oh, hey, I think it just came in. Let me check that. Give me a moment. I'll just take a moment to do this here. Sorry. Okay, hold on. I'll be right back. I need to, actually I can just send a message. To my wife here. He's unhappy now that he has to go into school. I can hear him moaning in the hallway. Like I said, I'm not quite ready yet, so give me a moment here to get all loaded up. Actually, I'll be right back. I'll be right back. Okay, now all that home domestic stuff is taken care of. We can get on to what we're doing here. Sorry about that, folks. Oh, the joys of working at home. Actually, I don't mind it at all. Most of the time, things go pretty smoothly. my desk is not high enough. I keep looking down, going, this is awfully low. So let me just raise it up a moment. You're going to hear the whining of the motors. There we go. That's better. Okay, where are we today? We were going to talk about the CSI assignment and just see how you're doing on that. Sounds like, Chris, you're already done, but Mary, you got a chance to work on it over the last couple days?
Yeah, I'm kind of lost.
Okay, maybe we can help you out.
Do you want me to just like share a snippet of my code, like take a picture of it?
Sure.
Okay. Let's see here. Like, I got some of it done, but I'm not even sure if I'm doing it right. So let me...
You're taking a screenshot and you're going to send it in the chat? Okay. Okay, here it is. I'm just waiting for it to appear on my screen. Go. Okay, let's see what we got. So tell us what's happening.
Sorry, muted. So the for loop, we're supposed to iterate like by 512 bytes, right?
Mm-hmm.
Okay. So that's what I did. And then so with each one, if the first 4 bytes match the bytes of the JPEG, then okay, we're like, hey, we found one, the start of one. So I guess I try to make a pointer, start of image that points to the address. I'm not sure if I did that right, or the integer where it starts. And then I started my, oh my gosh, I'm confused myself here. So, and then I guess what I did next in the first while loop is that it checks to see at the end of the block or the start of the next one, if the value at the byte before it is 0, and if it is, then it goes back all the way till it meets the end of the image. That's what I was trying to do, but I don't know if I did it right. And then with sprintf, I was reading about it, researching it, but I'm still confused. So that's where I am.
Okay, so do you know if this condition is working?
Yeah, because when I did count, like I put a variable in there and I printed it out, and it said it was 29. So I'm like, okay, well, it found the start of 29 images, so that must mean it's right.
All right, that's a good start. It's a very good start. That's probably like half the battle right there, actually, is just making sure you've got the right number of images. So did you get any compilation errors when you were doing this?
Yeah. But what I did, I was plugging like just random variables to like test. Like, for example, I tested, I guess I did like the length or something, the length value, and it was coming on like negative. So I'm like, well, that doesn't seem right. Yeah. But I was like, why don't we, because I thought what I was in my head thinking, we're iterating like by one byte until we reach the end of the image, not like, and it should be less than the 512 that it's going through. So it's, I feel like there's something wrong there.
Okay, so I guess, where do I start here? So this statement right here, that's, I mean, I see what you're trying to do here. You're trying to record where the image starts. And so you've got the right idea there, but the syntax of this is not quite right. So, so data bracket I, that's an individual byte. And you want to know what's the address of that byte so that you can store away its address. So to do that, you'll need to put you know, an ampersand on the front of it to get the address of it.
And would you remove the little asterisk then?
No.
No.
No. And then the other thing is this is not an integer pointer. This would be a u int 8_t. That's, because that's the type of the array right here.
Let's see. Okay. Let me see here. That change. So the ampersand, or not ampersand, the asterisk, doesn't it? It dereferences, right, the address. So that's why we do unit of 8 integer, right? Because it's pointing. So basically what it's saying is, here's the address, but also I'm giving back the value in there, which is a 8 by 8-bit integer.
Right. Okay. Because this is an array of 8-bit integers. The type of this variable here needs to be an 8-bit integer pointer. See, the star is still there.
Okay. I don't understand why pointers are like difficult for me to grasp. Like, it's so easy. Like, I understand the fundamentals. It's just like when it comes to like putting them in code, it's like all of a sudden I don't know what to do.
I don't think you're alone there at all in getting your head around them. And part of it is just, I think there's two parts of it, is just, first of all, understanding what they are, that they're addresses in memory. And then the other part is getting the syntax right so that the types match up. And I think that's two separate conceptual curves to get over. Okay. So the first part is just understanding what they are and what they can be used for. And the second part is being able to express that concept in the code itself. Chris, do you have any suggestions about where to maybe go from here?
I think after that point, I'd look at the next section, which is the first while loop. And
this one here.
Yeah. And maybe think that through as to what it's doing.
Yeah, so basically what I was doing, it checks. Well, I guess that wouldn't work. Well, would it work for the first case? It wouldn't, because a equals 0. Well, I don't know.
Do you remember this picture that we were drawing yesterday?
Yeah, I actually made my own little diagram to help me visualize.
Good, good.
um,
So let's say this red rectangle represents a JPEG that you found, and you've correctly located the start bytes. So that's what this condition up here does. So once you've located those start bytes and you're inside of this loop, the next thing that I think probably Chris did was to now start scanning forward for the next start sequence. So there's another, let's say there's another JPEG right over here. Right, so go into another loop, is that right, Chris? And you've kind of started it here.
Right.
So go into another loop in which you start scanning forward for the next start sequence. So you're going to basically have this condition all over again within that loop, but you're scanning for the next one.
okay. So, and you're just going to pass all that empty space. So once you get to the start of the next one, then you go back?
Yeah. Then you have another loop that starts going backwards and locates the ending sequence.
I see. Okay. So basically you turn, like, you would do a while loop that goes all the way through until it finds the start of the next one. Then you do another while loop that goes back to find the end.
Right.
Oh, okay. That makes sense.
So maybe as a suggestion, instead of perhaps storing away a pointer to the start of the image, which is fine. I mean, that'll work just fine. But you could also just store away the value of I, which is the index of the start of the image. And it's only when you get down to finally saving the JPEG do you actually convert that back into the pointer that you need to pass into save JPEG. But it might help to just store away numbers rather than addresses. And I saw Chris kind of nodding his head like, does that kind of make sense?
Yeah, at least in the code so far, I never changes. So you'll still have it available at the end.
So instead of doing this whole line here, you could do instead like int start of image equals I. Okay.
So, but doesn't I change with the bigger for loop? That's
yes. Yeah.
But we're saving the image within the for loop. Is that what we're
Because
doing?
eventually you're going to need to call save JPEG, and you have to pass it. Where does the image start, and how long is the image? So you're going to have to remember where that image started.
Okay.
But then your inner loop here could be something like int. I don't know what I'm going to call this. We'll just call this like J, right? Equals start of image. And then you can say while J is less than size, if all this stuff, right? But now instead of using, so basically it's this one right down here. Is that making sense?
Yeah.
Right? But now you're going to use J instead of I.
Okay.
So
because that would keep it moving.
Yeah.
Because if you just use I, it would just stay in one place, right? It would just be going over the same image.
Okay, so now you're scanning forward for the next start of image sequence. And then once that condition becomes true, now you've found that start of image sequence, and you can say int, whoops, wrong color, int start of next image equals J. And then you can start your next loop. While, let's call this k, right? Is greater than 0, or greater than image. If, and then another set of conditions for looking for the 2-byte sequence that's the end. Am I making sense here?
So, okay, so, sorry, there's just a lot to keep track of here. Okay, so basically in the first while loop, okay, so sorry, it takes me a while to like grasp all this. Okay, I see.
Well, let me write down some notes here. So it might help to maybe jot down some ideas that you've got here, which would be first scan forward a block at a time until the start of image sequence is found. Okay, and you've got that handled already. That's done. Once you've found that, then scan forward from the start of image to find the next start of image. Okay, so you've got one loop here that's looking for the first start of image. And then you've got another loop that starts from that point and scans to find the next start of image.
And that one should also scan a block at a time.
Yeah, that one can start a block at a time as well. So now you have the start of image of image 1 and the start of image of image 2. So you've got two start of images. So scan backwards from, we'll call it start of image 2, to locate the end of image 1.
Yeah, that makes sense. And we need to, that's why we have to increment every variable, because we need to actually go forward through the whole file.
So like this loop up here could be using I as its counter to move forward through the array. And then this loop could use another variable, we might call it j, as its counter to move through the array. And then this loop here would use perhaps a third variable to keep track of its counter as it's moving backwards through the array. Use I as the counter. Use j as the counter. Use k as the counter, or you could use other variable names that made more sense to you. So when you get done with these three loops, you essentially now have I pointing to this one here. You've got j pointing to this one, and you have k pointing to the end of image.
So basically, your save file, I mean, you would know that the image would be between the address of j and k.
The image would be between I and k.
I and k, sorry.
Yeah. So you could basically just subtract I and k and get its length.
Okay.
And the address of I is where it starts. Or the address of data bracket I is where it starts. Is it helping?
Yeah. Yeah, it is easier. Like sometimes I have to draw things out for me to understand it.
Absolutely.
It's hard,
I always,
you know?
I always
Yeah.
start with a picture.
Yeah. It's just like my struggle is how do I put that in code?
Yeah.
You know. Okay. So basically when we call to save it, well, we have to call sprintf. And I was confused on sprintf. Because I mean I was watching like videos about like people were just using like blank strings, and basically sprintf, it basically puts, instead of putting it to standard out, it puts it into like the array that you made. But you make to save the file. Is a file basically an array? Like I was kind of confused.
Say that again?
Is a file like an array?
Kind of. The file itself you don't access as an array, but this is just the file name. It's just the name of the file that we're going to call it. So this is just a string.
And what sprintf does, doesn't it just like put that information into the string, right?
Right.
Instead of like putting it to standard out, it puts it into that file.
Correct. Well, not
Okay.
put it in the file, it just puts into that string.
The string, sorry.
Yeah. And then you can use something like this. So here's the string that I want to build. I want to build it with the word image and then a number and then .jpeg. And then I've got some counter variable that's keeping track of how many images I found. And then it puts those characters into this file name string, and then you call save JPEG. And you might give it the address of data start of image, and then its length, which could be, in this case, k minus I, and then the file name. But you know, before you did save JPEG, I would, if I was developing this, calling save JPEG would actually be one of the very last things that I concerned myself with. Probably before that would be just printing out on the screen what you've found, right? Printing out, like, where did I find a start of image? Where did I find the end of image? Where did I find the next start of image? And just looking at and the numbers will be fairly large. They'll be like, you know, in the hundreds of thousands or millions. But the thing you're looking for is, are they coming in the correct numeric order, right? Is the start of image coming first, and then the start of the next image, and then between that is the end of the image, right? Are those three numbers kind of in numeric order? And then when you find the next image, make sure that the start of image of the second one, you know, corresponds to, what am I trying to say? When you find the next image, right, make sure, in other words, when you move on to, I'm done with the first image, right? I've saved that one away, although I haven't called save JPEG yet, but I'm basically done processing that one. And now I'm moving to the next image. Everything's just going to leap forward, right?
Yeah.
So now you got a new set of variables, but one of those variables should be the same as the previous one, because now you've moved forward to doing this one here. But now the start of this image should be the same as the start of the image you found when you were scanning forward for this one, right? So you're just kind of leap forwarding to this one. I mean, those are all things that you would just look for. It's just making sure the numbers look reasonable. And then, once they look reasonable, then worry about calling save JPEG. That's what I would do. Or once I was sort of confident that I thought those 3 loops were working and finding those 3 points in the file, then I would get around to calling save JPEG. And you could just maybe not worry about the sprintf. You could just save it as image.jpg, and you only get 1 out of there, but at least you got at least 1, right, that you can look at.
So save JPEG, is that like, are we saving the whole file, or are we just saving all, like, are we saving all the images, or are we saving 1 image per each file? Because I'm kind of
one image per each file.
Okay.
So every time you call save JPEG, it writes 1 file.
That helps. I think I get it.
All right.
What I'll do, I'll definitely work on it today.
Sure.
And
and don't forget that we do have tutoring and we have lab assistants available, so you can get some one-on-one time with a student who's actually done this assignment before. So they've been through all they've been through the whole process, and they can kind of help you out with making progress on it and show them. You can share your screen with them, and they can work with you and get through this.
Okay.
But
Thank you.
So Chris, did you kind of do what I described, which is what someone would call instrumentation, which is basically just dumping out data as the program is going and just looking at the numbers and making sure they kind of make sense? Did you do that?
Yeah, the first thing that I did is sounds like the same thing that she did, is I went through and printed out every start of image marker that I found throughout. And that finds the number 29. And then I also went and added to that, I printed out every end of image marker that I could find. And I knew that some of them wouldn't be valid. Some of them would be, I'd find that character sequence somewhere inside of the regular image data. But I just wanted to visualize and see what's in this file. What do I get back? Mm-hmm. And so you get more of those, but the last end of image marker before the next start of image, that would be the one, that's the one you're looking for. So I kind of have a picture of, what does it find in this file? And then what did I do? I drew myself several diagrams like you have down at the bottom there. Mm-hmm. I drew several different scenarios. So one was pretty similar to what you have there. Another was if there was a file that was all contained within a single block. I did another diagram of what would happen if the file ended in the very last block of the array. And then I went through and figured out how would I, if as a human being, how would I solve it? And I kind of did little diagrams to see how would I walk through this and backtrack and figure it out. So I did a bunch of that sort of work before I started writing code. Yeah.
So did you find anything helpful out of there, Mary?
Yeah, thank you.
So this is definitely an assignment where there's not like a clear cut, this is how you do the assignment. I left it open for creative thought on how to approach this problem. And it's I did that deliberately so that you would get a chance to really just kind of think about this and methodically break down the problem into these smaller pieces and tackle each one of them separately. And the first part you did really well, of finding the start of image of all of the images. And the next step is, okay, now find the start of image of the next image and then roll backwards from there. Does that help?
Yeah. Thank you.
And you're not the only person that struggles with this. I've been doing this assignment for a while, and lots of students work really, really hard on getting this, and not everyone tackles the problem in exactly the same way. It's just the technique that I showed you with going forward to the next image and then rolling backwards works pretty well for most people. It's just, like you said, a matter of getting those loops down and keeping track of all the variables that are holding on to information about where you are in the file.
Yeah.
And I'll actually, how about this? I'll give you and anyone else who's watching this a really big hint. As I've said earlier in the previous session, most JPEG viewers, when they hit that end of image marker, they'll just stop, right? They don't care if there's any data beyond the end of image marker. When they encounter the first one, that's the end of the JPEG image as far as it's concerned, and it just displays it on the screen. And none of the JPEGs that are in the file are larger than about 1.5 megabytes, 1.5 million bytes. I think the largest one is somewhere in that ballpark. So what would happen if you just called save JPEG, and instead of calculating the length here, you just passed in a number like 2 million? What would happen? Chris, you're smiling. What do you think would happen in that case?
The image, right? Or yeah.
The first part of you got chopped off. What did you say?
You would have the image, right? Because if it's 1.2 megabytes. But then, I'm sorry.
Chris, what do you think would happen if you just, instead of calculating the length, you just...
It sounds like if you make the size big enough, you'd capture at least one entire image plus extra data, parts of the next images. But the viewing software would just read the first image out of that file and ignore everything that comes after it. So you'd have more data than you needed, but you should be able to view the image.
So if you just located the beginnings of each one of the images and then immediately just called save JPEG with that starting location and just passed in 2 million for the length, you'd end up with 29 images, and they'd all be exactly 2 million bytes long. But they should all be viewable at that point. Is that what you were saying? So all the files would have too much information, but the JPEG viewer will just stop when it hits the end of the first image. So that could be a way to at least feel like you're on the right track of getting the images out there. The files for the images will be too big, but at least they should be viewable if you have in fact found the correct starting locations for each one of the images. So maybe try that. Try just at least getting the images into files so that you can view them, and then worry about closing that window down and getting them to be just the right size.
So, but like if you, for the first file, if you saved 2 million bytes, wouldn't that corrupt the next file because you take data out, or?
Oh no, so when you call save JPEG, it's not actually physically removing the data from the array. It's just making a copy of it onto a file.
I see.
So no, it won't corrupt the next image.
That's what I was concerned about. So I was like, I
guess that's one thing you have to realize as a programmer, is that whenever you you very rarely actually destroy data in the computer. You just either overwrite it or you just make a copy of it. And in most cases, you're just making a copy. So there's very few things you actually do in programming that actually outright will take an array and destroy the array just because you pulled some data out. And when I say pull data out, I guess that's programmer speak for make a copy of that portion of the array, rather than physically pull it out and make the array shorter. Does that make sense?
Yeah.
I mean, I guess as someone who's been programming for many, many years, many decades, I kind of sometimes forget about what seems obvious to me and is not necessarily obvious to someone who hasn't been programming for as long as I have. And
yeah, it is kind of hard for me because I'm like just starting this.
Yeah,
and
well, I mean, we're all just starting at some point.
Yeah.
But I guess, you know, if I can stand on my, I don't know what you call the soapbox. It's not really a soapbox. It's a humility box. It's a box where I, as a teacher, have to take a step back and go, what seems obvious to me, because A, I've been working on it for so long, and B, when I started programming, the field of computer science was very different than it is now. When I started programming, we didn't have internet. We didn't have storage devices that could hold more than a couple hundred kilobytes of data. When I started out, where is it? I mean, we didn't even have these. These hold what, 1.5 megabytes of data? I mean, that was like a luxury. And they were also just hideously expensive. No, what we had were these old floppy disks, right? These 5.25-inch floppy disks that hold 140 kilobytes total on each one.
It's crazy.
And so it was, I guess, easier to understand that there was a distinction between the disk drive, and you physically, you put the media into the disk drive and you close a little door, and you can hear the heads, come down onto that media, and you can hear the disk spinning. So it's very obvious as a programmer then to know when data is being written to the disk and when it's being read from the disk, because you can hear it. It's like this visceral thing.
Yeah.
And you can hear the heads moving on the disk drive, so you know something's happening when you write to the disk and when you read from it. And so you know that when you write an instruction to the computer, like save this file to the disk, and then you run the program, and then sure enough, the light on the disk drive lights up, and you can hear the thing going. You go, I made a connection between what that command I wrote in my program says and what's happening physically on the computer, on the hardware itself. And nowadays, it's vastly different, right? The hard drives and the storage devices don't make any sound at all, right? There's no more blinking lights on them that let you know that activity is happening. And also we have lots of computing devices like phones and tablets where file systems and the whole concept of files have now, for the most part, been completely hidden from the user. That, what you see is no longer a listing of files that are on your storage device, but you just see maybe the listing of people you can call and chat messages, right? But internally they're being stored as files, but you're no longer aware of that.
Yeah.
And so to now so I as a teacher, and I've talked to other teachers about this, that we're seeing this shift in students who come in who have had extensive experience using computers because they've been using phones and tablets and stuff like that, but they don't know, and it's not their fault, that they don't know about the underlying what's going on. They don't understand anything about files and folders. Sometimes I say to my students, go to the downloads folder, and some of them have no idea what that is or where that is or what goes in there. And it's not their fault. It's just that operating systems over the years have progressed to the point where you don't usually have to worry about those things.
Would that be called is it like encapsulation or something, where it's like it's becoming so user friendly that even the users don't really know, it's like driving cars, well, how does your car work?
It's called abstraction, right?
Abstraction.
Yeah. So you're separating out how the details about how something works versus the interface that you've got to use that thing.
Yeah.
And so you're right, the typical abstract interface is talk about like the steering wheels and the pedals and the key to turn it on. is a nice, convenient user interface for all the millions of parts that have to move in concert with each other under the hood, and you just don't have to worry about that. You know, the vast majority of people probably have no idea how an engine works, couldn't, let alone fix it if it broke. It's not their fault. It's not like they're less of a person for not knowing those things, but it's just the way things go. And so to hear you say, you know, I don't quite understand what's happening here in save JPEG, and I don't understand, am I writing to the file here? Or, you know, it just, to me, I was listening to you going, oh, wait a minute. Maybe that's a little gap in your knowledge, that you haven't made that connection between, there's a difference between a file name and the file that's on the computer and the content of that file, right? And so, again, I'm not trying to criticize or say, you know, you're less of a person for not quite understanding. It's just that you've never really had to deal with that.
No.
And I think teachers these days, computer science teachers are kind of wrestling with this idea. It's like, should we kind of take the students and say, like, here's what's really going on. You need to understand about files, and you need to understand about file names and distinction. Or should we just say, you know, we don't worry about those things much anymore. Is it really important to the core programming concepts? And we're kind of in this transition area, I think, where we're kind of trying to wrestle with that idea of, like, do we take a step back and say, all students now need to go through like remedial computer science training to explain some of this terminology and, you know, what's going on? Or do we kind of move forward and say, let's work on bigger things like artificial intelligence and networking? I don't have a good answer for you there. But it does kind of create this issue for me where I assume students know about files and file names, and maybe they don't.
Yeah.
So maybe I hope that some of the things in this class will help kind of illuminate some of those topics. But on the other hand, someone could come out of that going like, well, they talked about this stuff like files, but I still have no idea what they are. Well, I kind of wrestled my way through the assignments, and I kind of got it done, but I still don't know what they are.
Yeah. Well, I am taking IT and a Unix class, so that is helping me kind of, because honestly, all I've been doing so far is just coding, and it's like, I literally don't really know much about that, but now that I'm doing IT and Unix, it's helping me like, oh wait, that makes sense. So
yeah. And I guess the Unix class can help, but again, it's all like remote, right? You're just staring at this screen of text, and something's happening somewhere else. And again, it's not that hands-on feeling, like you don't hear anything, you don't see anything happening. I remember when I was working as a system administrator back in the 90s, we had Unix systems that were doing email and web serving. It was all just really, really primitive by today's standard, because the internet was really just taking off. And even though most of the time we sat in our office with our screens and these terminal windows that gave us a picture into what was happening in the server room, which was just next door, well, every once in a while I would walk into the server room and go, oh, I can see that computer is really busy right now because its activity lights are just like on constantly. And there was something for me to look at and go, okay, I know there's a problem here. I need to go back and figure out why the server is overloaded with too much stuff to do. But again, with the Unix class, you don't see any of that stuff. You don't see the physical machine anywhere. It's probably, I'm guessing that machine is either in Oregon or in Fremont somewhere. So we can't even go and look at it if we wanted to, because it's just too far away. So it's a good conversation to have, and it gets me thinking about, do I need to include some more kind of conceptual stuff? Like, I know in your Computer Science 10, the Introduction to Computing class, hopefully they went over things like parts of a computer and RAM and you know, storage devices, but maybe since you don't have any real world, or some students, I'm not saying you particular, I'm talking about you in general, the generic you may not have any practical hands-on experience with that kind of computing device. It still doesn't click in your mind because you can't make the connection between what we're trying to teach you and something you've actually experienced.
Yeah, no, that is an issue. That's why I wish some classes were on campus.
Well, it's also why some teachers, and maybe myself included, go like, that's why those kinds of old computers there were great learning devices, because they were so hands-on, and because everything you did on the computer had some almost immediate effect on what you saw on the screen. I don't have a good answer to that. Boy, well, all of my talking to you has lit up the YouTube chat. Let me see if I can catch up on some of that. So one question was, how much is someone said, I remember the floppy disk. Yeah, we used them for a while, then switched to USB flash drives. Well, how much RAM did the computer have? So my very first computer, very first computer, which I'm looking around because I think I have it in a box somewhere, but it's in my closet, and my closet right now is a mess. So I cannot show you my very first computer because it's in there somewhere, but basically it was, oh, I can show you a picture of it. How about that? So this was my own personal very first computer, the ZX81, or as people in other parts of the world would call it, the ZX81. It was about the size, it was about this big, about 8 inches by 8 inches. It had a keyboard, it was just called a membrane keyboard. So it's just a flat piece of plastic, and you had to press really hard to get the buttons to make contact on them. And this computer had, get this, 1 kilobyte of memory. 1,024 bytes of memory. And you plugged it into a television. In order to view it, you had to go, find a, and back then a big television was like 19 inches. That was a big television. But normally you'd have like a little 14-inch television. Plug it in, and it would show you this black and white display, black and white text display. You could do primitive graphics on it, very primitive graphics, but it was slow. It was so slow. So that was my very first computer. I got that in 4th grade. I saved up for that computer. It cost me $100 to buy that computer. And then I guess my first real computer was the Apple II. Look kind of like one of these things here. I don't have that computer, but I have one just like it in my closet over here. I'll show you that to you sometime. Maybe not today, but I'll show that to you sometime. Fire it up and actually start programming on it. So that was my very first computer. And I have to, I guess, thank my parents, because looking back, a computer like this was really expensive. The actual just like base computer here was probably about $2,000. And each disk drive over here was about $400. And the monitor was another maybe $200. So just for this setup, $2,000, $2,800, $3,000 for a computer like this. And this would have been like, so $3,000 back in the 1980s is probably equivalent to $6,000 to $8,000 today. So imagine you're a family and you're going to spend $6,000 on a computer. I mean, today you buy a top-of-the-line computer and it costs you, what, $1,500 to $2,000? Imagine spending $6,000 on a computer, and just one for your family. That would have been an incredible sacrifice that my parents made to get a computer for the family to use. And this computer had 64 kilobytes of memory and had disk drives where you could store 140 kilobytes on each one. And so that was the computer I used all the way through high school. And then finally, when I went to college, I got a Mac Plus. Looked like this. One of those little compact Macs. And that carried me all the way through about the first 2 years of college. And then I started moving up from there to, you know, as I was able to kind of increase my earning power by getting jobs, I was able to afford better and better computers as I went through. But each time I took a step up, I got more memory, more storage. And it wasn't really until we got to about 1992 when we really got a taste of what the internet was like. Back then it was very, very primitive. It wasn't anything like we have now. Didn't have the World Wide Web. All we had really was just the ability to send files back and forth and send emails. That was about it. So the computing landscape was very different in the 1980s than it is now. Right now, computing is like ubiquitous. Everyone's got a computer. Everyone has multiple computers. You keep one in your pocket, keep one in your purse. You got one on your desk. You got one by your bed as you're, for reading at night. You got, you got multiple computers just for yourself, and then everyone else in your family also has multiple computers. And back in the 1980s, you would have had one for the entire house, if you could afford it. No, I did not use the legendary Commodore 64, although I have one. You can't see it. It's way up there on the ceiling. It doesn't work right now. I have to fix it. Believe it or not, computers actually do break down over time. Very, very few moving parts, but they do break down. Some of the parts in there are just kind of like they leak their guts out of them. They have to be replaced. Plastic breaks. Sometimes the little copper traces get eroded and they have to be fixed. So they do have to be fixed, and that's kind of like my hobby. When I'm not teaching, I try to fix old computers. Let's see. Let me catch up on here. Oh, so the question was, do file names get stored in a database and point to an address on disk? Essentially, yes. That is what happens, is the file gets written to blocks on the disk drive, and then there is a special file up at the front, meaning up near like block number 0, that's basically a table of contents that gives the name of the file and then what block that file starts on. So it's basically a pointer that says go to like block 6 and you'll find file X there, and go to block 8 and you'll find file Y there. Don't have a solid background on the basics, but I suggest that you put out a series of videos about it. Oh my goodness. I don't even know where to begin. Like, what would you consider to be the basics? I'm not even sure. But there's plenty of YouTube channels out there where you've got people talking about like how to build a computer from scratch. I mean, literally, not like go to Amazon and buy a video card and a disk drive and a main board and a case and plug it together. I mean, like, build it from scratch. Like, go and purchase the chips and the processors and the RAMs and wire it all up. There's some great YouTube channels out there where people doing exactly that. That's a great way to learn if you can get the resources to buy those parts and put them together yourself. There's like there's Ben Eater, who does a great series on YouTube. Let me bring it up here. Well, we'll get to today's content here, but I got so many questions.
For many years, the most common way computers displayed information on.
So he's got a whole playlist on like how to build a computer from scratch, building a CPU from scratch, so actually building the the registers and the arithmetic and logic unit and the counters, doing all that from scratch, and building a video card from scratch. It talks to you about, you know, signaling, how basic networking works. This is a great channel, and lots of stuff to look at there. And he even sells some kits. You can buy some kits and you can build a computer from scratch. And then there's also the Gigatron computer. This is not a channel, but this is actually a computer that you can purchase, again, a kit for, and you can build a computer from scratch. And this computer doesn't even have a microprocessor on it. You just build the parts for a microprocessor, and by the end, you've got a computer that can play like Tetris and a driving game and something like Pac-Man. So you got a little computer that you actually can program in BASIC, and you built it yourself. What is this? I can find things in pawn shops and get rich. The problem is that you go to something like a pawn shop and they know how much these things are worth, right? So they're not going to have old computers that are there for $5. They're going to go, well, they search on eBay and they go, they know these things are worth a couple $100. So they're going to try to get top dollar for it. The place to find old computers is at you know, yard sales, garage sales, where somebody goes like, I found this thing in the attic and I have no idea what it's worth, so I'll sell it to you for 20 bucks. Okay, I'll take that. Thanks. Or go to e-waste places where they have old computers that are being recycled. And you go, can I have that? I'll take that one. Okay, so we wanted some like actual material today. What was I going to show you? Oh, I was going to show you how to use the debugger. And what else? I already forgot what we were going to do today. Oh, version control. That's probably the most important thing because we actually have an assignment dealing with version control. Okay, so with the version control, actually, I'm not going to write this. I'm just going to type it. It'll be easier. So version control systems are intended to address some problems that programmers run into all the time. Problems like making regular backups of source files, collaboration, keeping track of changes to programs over time. See, a lot of the problems that programmers have to do with things like this. Like, I used to take a survey in my class, like how many of you, and this was when I had 20 or 30 people sitting in front of me, how many of you have ever accidentally deleted your program? You know, a few hands go up. How many of you have ever made a change to your program and now it doesn't work? Like it was working before, you made a change and now it doesn't work. You know, several hands go up. Or how many of you need to collaborate with other people in the class? You need to share your program, you need to work together. You know, a few hands go up. So version control systems are designed to address these issues that programmers run into all the time. There are several version control systems out there. Probably the most well-known one is called Git, but there's also Mercurial and CVS and some others. So the basic idea behind a version control system is the same no matter which one you use. And that is, periodically, as you're developing some software, you will tell these version control systems to essentially take a snapshot, take a picture of what my program looks like at this moment in time. And that's basically making regular backups of source files. And the whole point there is to keep track of the changes to your program as time progresses so that you can do things like go back to a previous version, something that worked before and is now no longer working. Or to just have a record that progress is being made as your program is being developed. Or maybe you need to share code with somebody else. You might tell the version control system to take a snapshot of what my program looks like right now, and then you can send that off to someone else, and they can pick up where you left off. So I'm going to show you the version control system called Git. Like I said, there's some others out there, but this is probably by far, the most well-known one. So as far as terminology goes, you need to know a few terms. So one is a repository. So a repository is the place where backups are kept. Every time you tell the version control system to make a snapshot of your current program, it stores away that snapshot in a separate directory or a separate database where it keeps track of that stuff. And that's called the repository, or repo for short. By contrast, your working directory is where you actually do your editing, compiling, and running of your program. So it's not where the snapshots are kept, it's where you actually do your work. So when you make a snapshot of your program as it is right now, that's called a commit. Okay, so making a snapshot is called a commit. And then sometimes if you want to roll back to a previous version, that could be called a revert or a reset. Or even it's called rollback sometimes. Now, in this course, we are using a version control system, not so much to collaborate, not so much to be able to roll back and roll forward through history, not so much to be able to do complex project management, but really as a way to do two things. One is to make periodic backups of your programs so that if you accidentally delete them or you accidentally make a change that is going to break it, you've got some way to go back to a previous version. And the second thing that it's useful, actually there's three things it's useful for. The second thing it's useful for is sometimes, actually quite often on these assignments, I need to give you some starter files, some either programs that have been half written and you need to fill out the rest of it, or maybe there's some data files that you have to work with. And using a version control system is a very convenient way for me to give you those starter files as a package. I can tell you to go to a website and essentially download the source files that I've given you, and that'll give you your starting files. Up until now, what I've had to do is just show you a page on Canvas, and you would say copy and paste this file into your editor, or download this file and then upload it to our IDE. But the version control system gives me a very easy way to dispense starter files to you. And you'll know that you have a working set of starter files. And the third reason to use version control system is the opposite. This also gives us now a good way to turn in your programs if you have to turn in a whole package of files and not just one file. So from now on, from this point forward in this course, you're no longer going to be turning in your programs by downloading your C file and uploading it to Canvas. You will instead upload your entire project for an assignment to a central website, and then just give me the address of where those files can be found. And then I'll be able to download your files, and I'll get a complete set of working files, and then I'll be able to compile and run your program and try it out from there. Okay, so the act of taking files from a central place and bringing it down into your working directory is called a clone. If there's an existing repository of files, you can clone that repository. You can make a copy of it. Sometimes cloning is also called forking. Right? It's the same idea. As you've got one repository, and from that you're now going to make two. You've got the original one, and you got a copy. Push means to take the files that are in your repository and upload them to another repository somewhere else. And pull is the opposite. Okay, I'll go over the workflow a little bit later. I'm just working through some of the terminology now. I don't expect you to understand exactly what all of these terms mean until you've had some experience actually using them. The question here is, what's the maximum file version? There isn't one. Right? Some version control systems will do file versions with just an incrementing serial number. So you've got version 1, version 2, version 3, and those just go forward. And the only thing I could say about that is there probably is a limit. It could be the version number is like probably just an integer, which means the highest version number is likely to be around 4 billion. Or maybe it's a 64-bit quantity, which means the highest version number is way huge number, but you're unlikely as a programmer to ever run into that limit. Git doesn't use version numbers in that sense. It doesn't use serial numbers. It uses basically random codes as version numbers. They're called hashes, actually. So it takes your repository, it runs it through this algorithm, and it out pops this giant like string of digits, and that's your version number. So they're not in any numeric order, but it is a unique identifier for that version. So you can refer to a version by its unique identifier, which is this long string of digits. And there's really no practical limit at all. Well, they're not technically random, but they appear random to us humans because they're not in numeric order. Okay, so that's the terminology that you need to be able to work with a version control system like Git. So let's do some examples of this. So the first thing you have to get your mind around is that in a version control system, you've got to be a little more organized about your files. From this point forward, I would encourage you to put all the files related to a single assignment into its own directory. That way everything is together, and you can put all the files in that directory under version control and ignore all the others. So let's say we're going to, well, I guess what I want to do is I want to take, let's just do this here. Let's create a new folder. And we got to give this folder a name. So usually usually it would be the name of an assignment. Like you might call it, level 5 or something like that, because this is the assignment for level 5. Or you might call it, warm-up 6, right? Because these are all the warm-up assignments for number 6, right? So let's trying to think what's the best way to do this. Should I start from scratch? Well, actually, let me do this just so we can jump ahead so far a little bit. Let's say I've already got this folder here called image that contains all of these programs for working with images. Should we do that? No, I think let's not do that. Let's just go ahead. Let's go ahead and create a new folder. So let's call this, I don't know, let's call this, I'll go ahead and call it level 5, okay? So I've got this folder called level 5. And now what I want to do is start my program in there, in this level 5 directory. So here's something you can do in our IDE. You can actually open up a new window that contains only a view of that level 5 folder. Now I think this is actually a really good way to do this. Is you can right click on that and you can say, where is it? Nope, it's not there. You can go over here and say open workspace. And we're going to pick level 5 and click on open. And now I've got a separate tab that is only a view of that level 5 folder. You can see there's nothing there. I've got this other tab that still has my view of everything. But over here is just my level 5 folder. And I'm going to encourage you to do this for a couple of reasons. One is, first of all, it allows you to focus on just that one assignment. And secondly, it actually makes working with the version control system easier if you open up a separate window just for this folder. So let's go ahead and make a new file. And let's just call this like hello.c. And let's start writing our program. Great, got my program. Let's go ahead and save it. Let's open up a new terminal down here and notice that my terminal is already inside of that folder. That's really great. If you were working in this tab over here, you wouldn't be in that folder and you have to do a little bit of Linux command line stuff to get into the correct place. But now I'm going to go clang hello.c and it seems to work. I'm going to run it and I'm satisfied that it's working. So at this point, this would be a good place, a good time to make a snapshot, a commit of my work. So before that, I've got to do a couple of steps. So first thing to do is, these are git commands. All the git commands start with the word git and then a verb. So the first one we want to do is git init. So the purpose of git init is to initialize the repository using your current directory as its working directory. So you just type in git init, press enter, and then you get a confirmation message back that says you initialize the empty repository, and it is referring to your level 5 directory. The next thing to do, and you only have to do this once, is git config -- user.name and then put in your name in quotes and then git config, oops, no, I got this wrong here, -- global username, here we go. And then your email address. Let's see. Git usually comes pre-installed on Linux systems, but on the Mac, you will probably have to install it yourself. What you need to do is if you install the Xcode tools, then you will get Git along with it. So if you've already installed Xcode tools so that you can get your C compiler, then you probably will already have Git installed as a result of that. So as long as you have like Clang and GCC, Git's probably already there. You can find out easily if you have it. Just type in Git, and if you get back a message that looks like this, then it's there. If you get back a message that says command not found, then it means it's not there. Okay, so let's go ahead and git config -- global user.name. Put in my name here, and then git config -- global user.email. So Git does not actually care what name you put there and what email address you put there. It's not going to verify them. It's not going to check at all. What that's there for is if you're collaborating with someone else, then that person you're collaborating with will know how to get hold of you about the buggy code that you just turned in. Okay, so now we're ready to do our first commit. On Git, doing a commit is a two-step process. You need to do a command first called git add, and then git commit. So if you don't have Git on your Windows system, you can get that pretty easily. So if you're not using our IDE and you're using this on a Windows system, I'm talking to the YouTube folks that are following along here. If you go to git-scm.com, here it is. This is the website you go to, git-scm.com. And then you should, so right over here, I mean, obviously I'm on a Mac here, so it says download for Mac, but that's not what you want. You go to Windows Build here, and then you can download one of these setup programs for your operating system and get Git for Windows. Okay, so we're going to go git add hello.c. And what that does is it just tells Git that I'm going to be committing this file. It just marks it. It's called staging. It just marks it and says, when I do a commit, this is going to be the file I want to do. The idea there is that you might have several files that you need to commit, and you're going to mark each one of them. You're going to say, I want to do this one, I want to do this one, and this one, but not these other ones over here. So maybe you have your hello program, and maybe you have another program that you're working on, and you want to commit both of them. You need to mark both of them to be committed. If you only want to mark one of them, but not the other one, you just add the one that you want to commit and ignore the other one. And then we're going to go commit, and then you want to write a little message. So it's important to put this -m, and then in quotes, put a little message, a little one-sentence reminder about what this commit is. What changed between this commit and the previous one that I did? Now, I haven't done a previous one, so it's okay here to just say something like first commit. And now we have made a backup of my program. So let's go ahead and make a change. Let's put another print here. And before I do a commit, I'm going to want to compile and run the program and make sure it works. Good. So I'm satisfied that at least it compiles and runs. So I'm ready to do another commit. git add hello.c, and then git commit -m. So what changed between this commit and the previous one? Added comment, or added second print statement. So this is kind of your workflow. When would it be a good idea to do a commit? I would suggest a good time to do a commit is a couple of places. One is when you're done doing your programming for the moment, like you got to go get lunch or get dinner, do a commit, because you never know what's going to happen between now and the time you get back to your computer. I have so many stories from students about they were, all they did was just got up to go and, drive to school or something like that. And along the way, they got into an accident and their computer broke, right? You never know what's going to happen. Particularly in a work environment, you really never know what's going to happen. So it's always a good idea when you're kind of done coding for a while, do a commit. The second time you might want to do it is just periodically as you're doing coding. You got to a point where maybe you've made some progress on the program. You reached the point where it's not complete, but at least you added a new feature or you added a new section of the code that you wanted to accomplish for that coding session. And it compiles, it runs. Again, it's not complete. It might still have a bug in it, but at least it works. Do a commit at that point. Doing a commit, as you've seen, is a really inexpensive process. You just type in git add and the name of the file name, and then git commit and a little message, and that's it. Git is really trying to reduce as much friction as possible between you, the coder, and making backups of your programs. There's no downside to making too many backups, but there's lots of upsides to it. What would happen if you don't put the -m option on there? Then what happens is it throws you into a little tiny text editor, and then you can type in your message there, but that's more trouble than it's worth for me. Particularly if you don't know how to use that little text editor. It's not like this text editor up here. It's like a little text-based text editor, and you have to know how to save and how to get out of it. And so I would at this point just do the -m. Let's see what happens if you don't do it. Let's make another change. I see that I misspelled beautiful here. So let's go ahead and fix that typo. Let's recompile it and run it and make sure that it works. That's good. So we'll git add hello.c and then git commit. And now you find yourself in the Vim editor. And here you would have to know how to get yourself out of it. So the way you get out, by the way, if you do that, is you type in colon and then Q, enter, and then you're out. And then go ahead and rerun the command with the message. And you can change what editor gets put up there. What I really like to do is figure out how to get it to understand to open up the file within the editor up here. If I could get it to do that, that would be awesome. And then we could just type in the message in this editor, save and close it, and then you'd be done. Okay, so that's the general workflow here is you only have to do the git init once per project. And that's only if you're creating a repository from scratch. If you're cloning an existing repository, you don't have to do the git init because it already made a repository for you. You have to do the git config just once, forever. So you don't have to do that ever again, at least on our development environment. So the only thing you have to worry about is just doing your commits. What would be good files to commit? Should I commit the a.out file? What do you think? Should I commit that? No. Chris is shaking his head. No. Shouldn't commit that. Why? Because you can build it again out of your source files. Basically, any file that you can build out of other files, you probably shouldn't put into version control. So you should put in there any files that make up the base of your project. C files, header files, maybe any images that are needed by your project that are required for using it, any data files that are required for using it, everything else, executables, assembly language files, files that are written as a result of running your program, probably should not be put into version control because you could always rebuild those later on. Some more sophisticated development environments have version control and the build and compile project integrated together so that it can do things like enforce rules, like it will not let you check into version control, will not let you commit into version control any program that doesn't compile. So you run the compiler, it doesn't compile. You then go, well, I'm just going to do a commit anyway, and it won't let you. It'll say you can't commit source code that doesn't compile. Or some of them may be integrated in such a way that when you do a commit, it's going to go ahead and compile and run your program anyway just to make sure it works. But we are not set up to do that. We're doing compilation and running separate from version control, in part because getting it to integrate is a more sophisticated setup. And again, you start abstracting away the user interface from what's going on under the hood. I'd prefer at this point that you manually do all the steps. And then later on, when you get more sophisticated using version control systems and build systems, you'll learn how to integrate those things together. I know someone who works at Google, and there the version control system and the build system is extremely sophisticated. Like, you know, he works on the Chrome team, so he's responsible for programming the parts of the Chrome browser. And there, if you want to do a change and then do a commit, it's not just a matter of just going commit. You've got to like ensure that the change you're made actually runs, and so it runs this whole suite of tests on the Chrome browser to make sure it works. When you do the commit, it then marks that commit as being like pending, and someone else has to come in and review your changes and mark it as done. And only then will your change be allowed to be rolled into the actual Chrome product itself. So, you know, there it's a lot more sophisticated, but you can see why, right? They don't want just any random change showing up in the browser. Everything's got to be reviewed. Everything's got to be vetted to make sure that you're getting changes that work in the browser, and no one's trying to like put code in there that doesn't work. So why don't we take a little break? It's already 11 o'clock. We'll take a little break, and then when we come back from the break, I'm going to continue with this. I'm going to show you how to set up a remote repository where you're going to send your files to when you actually want to turn them into me. And it's also a place to keep backups of your files that isn't here in this development environment. So if something were to happen to it, at least you've got backups in another place. Okay, so about 10 minutes, and then we'll come back and we'll finish up this discussion. See you in a little bit.
Recording stopped.
Okay, wow. YouTube has like really been chatting away. Let me see if I can answer some of these questions. So I'll kind of maybe scroll up a little bit. See what we've got here. Okay, so on the Mac, two ways to get Git. One is to install the Xcode tools. And again, you probably already installed the Xcode tools if you were hoping to get the compiler and the build system. And the Xcode tools is not the complete Xcode environment, which is like 1.5 gigabytes. But you can do the Xcode command line tools and obtain just that. So it's not the whole build environment with the Xcode application. It's just the command line tools. And that's probably, for myself, that's what I have installed, just the command line tools. I don't need the whole Xcode thing because I don't do iPhone development and iOS and Mac development. I just write little programs in Perl and Python and C and C++. So the command line tools are good enough for me. You can Google how to do that if you haven't done so already. How to install Xcode command line tools. Well, that didn't help. This one says, to install the command line tools, just launch Xcode and tell it to install the command line tools. That's not what we want at all. Ah, here it is. So you open up a terminal, and then you, I think you do this one here. So the other way to install Git is to use a package managed system, a third-party package managed system called Brew. Actually, it's called Homebrew. And Homebrew is a great system because it allows you to install lots of other command line programs that aren't normally installed on your Mac and are otherwise difficult to get. So you go to this website, brew.sh, and then there's a command for you to run. You can copy this command, open up a terminal, and just paste that command in, and then press enter, and it might ask you a couple of questions. Like it'll ask you to enter your password. But along the way, it'll also install the Xcode command line tools. So Linux users really have it great, right? There's pretty much, every command line program you could need under the sun. But Brew was a way to bring a lot of those same programs and same command line utilities to the Mac. So you install Brew. I already have it on my system here. And then installing a new package is as easy as typing brew install, and then the name of the package. Or you can do brew search, and you can search for the thing you're looking for. Like if I search for Git here, for example. We'll go out on the internet, download a database, and then here is probably the one I'm looking for. And then I can say brew install Git. Now, the nice thing about using Brew or Homebrew is that you get the most current version. When you install the Xcode command line tools, you get a version from whenever Xcode was last updated, which might have been a year ago or so. If you do it using Homebrew, you will get like the latest version. So it actually doesn't hurt to have both versions installed. You have the one that comes with the Xcode command line tools, which is going to get installed for you anyway as a result of installing Brew. But then you do brew install Git, and you'll get the very latest version. There's not a whole big difference between the very latest version and the version that comes with Xcode, but some people are into having the latest versions. You can also do like brew install Clang and get the latest version of that. There's just, thousands of programs you can install that come through the Homebrew system as opposed to downloading the application off the internet and installing it yourself. So I recommend that route for installing things, at least on the Mac. And then on Windows, as I pointed out, you can go to git-scm.com and you can download an installer for your appropriate Windows version, and then you will get a Git that you can run on the command line. Also gives you a nice little context menu, so if you right-click on a file, the little menu will pop up, and there you can run Git commands as well. You can do things like Git, I think you can do basic things like commits and adds and pushes and pulls, And it will also let you open up a command line environment called git bash, which is basically the bash environment, but for Windows. And then from there, you can run your git commands on the command line. And then the third way to get git on Windows would be to install the Linux subsystem for Windows. Basically, go to the Windows, I think go to the Microsoft Store and search for Linux or search for Ubuntu, and it will install the Ubuntu operating system on your Windows system. And then when you, so it's basically Ubuntu running on Windows. So when you launch Ubuntu, you actually get a window where you can type in your commands, and then I think you do get things like git along with that. So it's nice to see that Microsoft is no longer this siloed, independent operating system that operates kind of like under Steve Ballmer, the former CEO. Steve Ballmer said, Windows is like the be-all, end-all operating system, and none of the others out there exist. And so he really wanted to do things like the Microsoft way for everything. And then under the current CEO, he's really opened things up and said, well, we do acknowledge that these other platforms exist. There's the Mac, and actually Windows has a huge history with the Mac. The very first versions of Excel and Microsoft Word came out for the Mac, not for Windows. Windows came later. So they really kind of like owe a lot of their history to the Mac. And so the current CEO says, well, these other platforms do exist. There's Linux, there's iPhone, there's there's iPads, there's Macs, and why don't we just go ahead and if Microsoft wants to be friendly to everyone, we need to embrace these other operating systems that are out there. So now they've got things like Visual Studio Code that runs on Linux and Mac and Windows, and they have the Linux subsystem for Windows, and they've really kind of embraced this idea that there are other operating systems out there that have their own advantages over Windows, and really just kind of brought them into the fold rather than just ignoring them and pretending they didn't exist. So you're trying to catch up on the comments here. Yeah, but I'll have to admit, I use Visual Studio Code quite a bit. I toyed with the idea of maybe using Visual Studio Code for this course, but I really like this idea of having a development environment for my students that is web-based, so there's nothing to install, nothing to keep updated. And I know that when everyone brings up their IDE, they're looking at exactly the same thing that I'm looking at. And I think that's, from a teaching point of view and a learning point of view, there's a huge advantage to having a consistent platform for everyone. And one in which there's no friction, there's no learning curve to get over. If you want to install Visual Studio Code, that's easy to download the application, but as it is, it doesn't do anything. It's an editor, but there's no compiler. It doesn't come with a compiler, so you'd have to install that as a separate step. And the instructions there for Mac versus Linux versus Windows would be different for each operating system. And then we run into a possibility of different versions of the compiler. And this was actually a frustration expressed by one of my colleagues at my university, that he had students using just the compiler that was installed for their particular operating system, which meant that the Mac people were using Clang, the Linux people were also using Clang, but a different version of Clang that gave different error messages, and the Windows folks had to use GCC. And so he had basically 3 different compilers and different sets of error messages, and he said this was just a big pain to deal with. And when I talked to him about developing this web-based IDE, he jumped on that. He said, that's going to solve all my problems about having different compilers for everybody. And I like that also. And a lot of my students have said they really like it because when they go to our IDE, then they can focus on just this course. right? They're not distracted by all the icons on their desktop and little notifications here and there. They're just working on our stuff. And the third advantage is it runs in a web browser, so you don't have to worry so much about what happens to my computer. If my computer suddenly breaks, then all the files are kept somewhere else, and I can go to another computer and just pick up where I left off. I kind of think that web-based development is perhaps where the industry is headed towards. Anyway, there will always be a place for doing desktop-based development because it could be faster. You could have more resources available to you, but the web-based stuff is, it's just really convenient for everybody. Even the folks at Google, they don't do development on their own computers anymore. There's a lot of developers at Google who just carry around Chromebooks. So when they do development, they are basically doing remote development. Their Chromebook is just a window into some server somewhere else. And they do development on that. And then when they go to compile, they can take advantage of the fact that there's multiple computers out there. They can distribute that compile across hundreds of computers. And a compilation process, if you compiled Chrome yourself on your computer, it would be download the Chrome source code, type in the command to get it to build, and then go take a long lunch. Like hours to build Chrome. But if you're actually at Google and you have take advantage of their farm of servers, you can say go build Chrome, and it takes a few minutes because it distributes that build across hundreds of machines. And then it collects all the executables that come back. But everyone has their own use cases, right? Sometimes web development is just not for you, or your particular tool set doesn't work on the web. So I'm fine with that. But I think for my students, this works pretty well. I'm all about how can we get to the core content of the course as quickly as possible and not have to worry about frustrating things like I can't get my environment to work. And for the most part, most installation, when I was using, or when this other faculty member was using their own IDE, he says, well, for the most part, 80% of the students, it worked fine. You install the IDE, you install the compiler, great, you're up and running. For 20% of the users, there's a huge problem. Something was not working. Not enough disk space. Because actually that ran into me one time. I had students installing something and they said, I can't install it, not enough disk space. And I said, what? What's going on? He goes, well, it's full of movies and music and stuff. I said, well, can you delete some of them? No. Why? They had their own reasons why they couldn't. Or we ran into driver issues. Something's wrong with the network driver. Something's wrong with the video drivers. Just didn't work. It was just a huge pain. So I decided to go all web-based stuff. So I think for the past 3 or 4 years, students in my classes have never had to install anything on their computers. Has it been 10 minutes already? Wow. It's already been almost 15. Okay.
Recording in progress.
All right, so we're going to pick up where we left off, and I'm going to show you, now that you got the idea about how to start a repository and do your commits, now we're going to talk about pushing those changes up to another repository, a remote repository, so that you can store your versions elsewhere. So there are some websites that provide repositories for you to use. There is GitHub, which probably a lot of you have heard about. There's also bitbucket.org. And there's a few others out there. There's GitLabs. So the idea is the same for all of these. It's to have a website where people can go sign up for an account, and then they will also host your repositories, copies of your repositories on their website. So there's some advantages to that. One is there's now a second backup of your programs elsewhere. Two is if you want to collaborate with somebody else, you do need a central place where both of you or whoever's on your team can go and access these files. And three, a lot of these websites have some additional tools for working with projects that Git alone cannot provide. They can do things like bug tracking, so users can submit bug reports. And there's collaboration tools, so you can talk to your team members. There's project management tools for tracking how long it's taking your project to do and when are deadlines. So there's lots of tools that these websites provide that the command line interface to Git itself doesn't provide. So a lot of people would say, well, why not just go with GitHub? And I have tried GitHub, and for me, at least my experience has been GitHub wasn't so good in an educational environment. That may have changed over the past couple of years, but when I first looked into it a few years ago, I talked to Git, and I said, what do we have to do so that my students can use Git? And they said, well, what you have to do is go onto Git, you have to create a group, a team, and then you have to put all of your students into that team. So basically type in all of their email addresses, and it will send out invites to all of your students. And then you can form a team, and you'll be able to start using Git. And I went, well, that's great. So that sounds like a lot of work on my part. Like I have to go find everyone's email addresses and copy and paste them in. And then if somebody drops the class, I have to pull them out of the team. And if somebody adds the class, I put them in the team. And at the end of the semester, I have to empty out the team and then put in the new students and re-invite everyone all over again. And I said, that's just a lot of work, because all I want to do is just have a place for my students to just upload their work. And so I turned to Bitbucket instead. That seemed to work a lot better in the educational environment. So the two websites have kind of different philosophies about what you can do with them. All of them have a free tier, and then all of them also have a paid tier. And the reason why you might want to pay is because you might be working on a very large team of people. You might be working on a team of 10 or 15 or 20 people, and to be able to host that many people all sharing the same repository, these websites all have to make their money somehow, right? Someone's got to pay the bills. And so a lot of workplaces do, in fact, pay for teams on these websites because it's cheaper to pay for that than it is to run your own server and hire an IT person and run the hardware, make sure it doesn't break, make sure there's enough storage and backups. It's just easier to pay $5 or $10 per person per month for a team. For the free tier, and again, things have changed over the years, but for the free tier, GitHub says that you can create your own repositories as long as they're all public. GitHub's philosophy is we want to host open source projects. We want to host projects that other people are going to collaborate on. So the repositories that you make for free have to be open source, have to be open to everyone. And that's not so good for an educational environment because, we don't want people to cheat. We don't want people to share code so much. Bitbucket, on the other hand, says if you're a small team or you're just an individual, you can create as many public repositories, private repositories as you want. You can create as many repositories that aren't shared with other people or shared with just a small number of people. You can do that all you want. If you want to work with more than, let's say, 5 or so people, then you got to pay. And I said, well, that sounds like what I want to do. I want my students to be able to sign up for an account, create their own repositories. They're only going to share it with me or maybe one other student in the class. So that sounds pretty good. And so I understand that things have changed over the years. So I think GitHub now allows people to create their own private repositories. But I'm so ingrained in the the Bitbucket ecosystem that here I am. Eventually, maybe I'll look into GitHub again and see if they can do what I want to do. And that might be a convenient place to go. So we're going to use Bitbucket. And to do that, you go to their website, bitbucket.org, and you'll create yourself an account. Now, Bitbucket also told me that if you sign up for this account using your educational email address, so for us it's the one that ends in sierracollege.edu, then they will upgrade you to the educational version, which gives you unlimited private repositories and unlimited collaboration. So they're essentially giving you the premium pricing tier for free. So sign up for this account using your school's email address, and then you will be upgraded to the educational version, which gives you many more features than you would normally get with the free version. Now, I've already got my email address, and actually, you know what I did is I signed up for this account using my school email address, and then I changed it to my Gmail address. Normally, once you've done this, you will just see a blank screen. You don't have any repositories set up over here. So what we're going to do is we're going to create a repository on Bitbucket, and then we're going to push our work from our workspace up to Bitbucket, and now we'll have 2 copies of our repository. So I know some of you are probably watching this and need to catch up and create an account. I don't know if I should pause for a moment and let you go through the whole account creation process, or if I should just push ahead and then you can come back and watch this later. Well, I'll give you a moment. The account creation process is the usual. Sign up for an account, it'll send you an email to confirm, click on the confirmation, and then you should be good to go. The upgrading to the educational pricing tier will come after you've confirmed your account. You will probably then get a second email that says you've been upgraded to the educational tier. Okay, so what we're going to do is once you get to the screen where, again, it looks a little bit different for you because you don't have any repositories already created. And I also understand that I've had my account for so long on Bitbucket that even my view looks different from your view, which is a more recent account. So bear with me and I'll try my best to replicate what you're going to see. But you should see a toolbar here on the left. If you don't, there's probably something you can click on to make the toolbar visible. And then you're going to click on plus to create something. And we're going to create a repository. So we already have a repository on our IDE. We're going to create essentially a parallel repository on Bitbucket, and then we're going to be able to move the files back and forth between them. So it asks you to fill out this form. Under Workspace, what I would do is I would create a new workspace. I think there's a way you can do that here. Create a new workspace and then call it, like, you know, Computer Science 46 or C programming or something like that. It's basically a way for you to take all of the projects, all of the repositories for a particular organization or for a particular unit of work and put them together. And so we're going to take all the repositories related to this course and put them together. So that's what a workspace is. So I'm going to put this under my computer science 46, and then my project. Again, you can have a project based upon semester. So I'm going to call this Spring 2022. And then finally, repository name. And you can make this match the repository name that you have on the IDE. We called ours level 5. Okay, next, make sure this box for private repository is checked. And then for include a README, make sure this is set to no. It's really important that you make sure this is set to no. This will ensure that your repository is completely empty. Otherwise, it'll have some files in there, and then the initial push that you do won't work. So make sure this is set to no. Default branch name, we'll go ahead and put in main, just like it suggests. Include the .gitignore. Please change this to no. And then click on create. So if that's worked, you should see a screen that looks like this. It says, let's put some bits in your bucket. If instead you get a listing of some files, and one of those files might be a README, and one of those might be a .gitignore, then it means you didn't check those boxes for no, and you should probably delete this repository and go and create it again. And the way to delete it is you click on repository settings, and down at the bottom, where is it? Way down here under settings? Nope. Every semester they move stuff around. Repository details. Advanced. No. Manage. Ah, here it is. Delete repository. They've moved it over to a menu. It used to be at the bottom of one of the screens. All right, so you go into the repository settings, click on repository details, and then under manage repository, you click on delete repository, and then you can start over again. Okay, but let's put in your bits in your bit bucket. Put some bits in your bucket. So what we're doing here is we are get your local Git repository onto Bitbucket. So this is what we are doing here. Ignore the stuff about creating READMEs and creating a gitignore. Please don't do that. Step number 1, switch to your repositories directory. We are already there. We are in that directory, so we're good. Next, connect your existing repository to Bitbucket. Just copy and paste these 2 commands. I'll copy that one, paste it in here. And what this command does is it connects the repository we have on our IDE with the remote repository that we've created on Bitbucket. So the 2 are now connected together. And the next command, paste that in. Type in your password. Oh, I remember now. They no longer let you just type in your password. You have to use what's called an app password. Let's see if I remember how to do that over here. Is it over here? Profile and settings. Personal settings? have to go here we're app passwords right here, app passwords. Okay, so what did I do there? So I went back to the Bitbucket website. I clicked on your profile and settings down in the corner. Then I went to personal settings. And then to app passwords. And then I create a password. I'm going to call this Git3 because I have 2 others, but you should probably just call yours Git. And then under permissions, you go to repositories here and just click on like read, write, write and admin. And then click on create. And what it'll do is it'll give you this long string of characters that you're going to use essentially as your password. So I'm going to show this to you here, and then since this recording goes out to the public, I'm going to revoke that password when I'm done, so it won't be the one that I actually use. All right, so here it is. So you should copy that down. Like, make a copy of this, open up some file somewhere, like on your computer, and paste that password in there so that you always have access to it. Okay, that's the only time you're ever going to see it. It's just on that little window. And then we'll go back here and let's do the same thing. Type in the password. I'm going to paste in that password and done. Okay, so that long string of characters and numbers, you should copy that away into some file on your computer, like a little, I don't know, you have like Notepad or some way to keep notes on your computer, and just paste that thing in there so you always have access to it. And then since I'm running out of time, what I'll show you next time is how you can actually have Git store that password away so you don't have to keep typing it in, or you don't have to keep copying and pasting it. But for now, I'm just going to say make a copy of that password in a file, and then just copy and paste it every time Git asks you for a password. Okay, so we've pushed our files up to Bitbucket. So now if we go back over here to my repositories, here's that level 5 one that I just created, and here's my file. So I can click on it and I can see the contents of that file. I can look at all my different versions here. So I can look at a version from my second version. I can look at my first version. So you have access to all of your different versions. So even if you haven't learned yet how to use Git to roll back and revert versions, at least you can come to Bitbucket and you can pull out of that menu the version you want to look at, and then you can just copy and paste, the section of code that used to work, paste it back into your program, and it's kind of like recovering the old version. So let's go back. One more thing to do is let's go and make one more change to this. Let's just change this print statement here. I'm going to save it, compile it, run it just to make sure it works. Good. So to do a commit, I'll do git add hello.c and then git commit -m added wonderful. And then now I can just say git push. I don't have to type in those 2 commands I had before, just simply git push. It's going to prompt for that password. I just pasted it in really quickly. It has now pushed it up to Bitbucket. And then when I come back over here to my source and refresh this, it should say that I changed this just less than a minute ago. And then I can see this now contains the very latest version. Okay, So let's go and look at the assignment for this week. The assignment this week is really easy. Should take you no more than a few minutes to do. So get a little break this week. Step number 1, configure Git. We already did that. Step number 2, sign up for a Bitbucket account. Please use your college email address so you'll be upgraded to the academic version. Step number 3, on the main Bitbucket screen, go to your personal settings, click on App Passwords, create a new app password, and check the 4 boxes for read, write, admin, and delete under the repository section, and then click on Create. Copy down that password that appears on the screen. Go back to your IDE window and initialize a working directory for, and what we're going to do is we're going to take all the files associated with Lab 2, Level 2, that you did way back at the beginning of the semester, and those are like the, what was those? Those were the, oh gosh, I don't remember what they were. Oh, they were the collats and the sigmoid function and making change, those 3 programs. So you're going to create a repository for Lab 2. And then you're going to move those files into that directory. Then you're going to add those files. Do a commit. Create the repository on Bitbucket. And then follow the instructions for doing your first push. You're going to paste in that app password, and it should push things up to Bitbucket. And then finally, you need to share the repository with me. When you share the repository, you're going to click on this ... menu in the top right corner of the screen and click on Share Repository, and then type in my email address. So I use my Gmail account for this course, and it's not my usual Sierra College email address. It's my Gmail address. So you paste in my email address and then click on Add, and then what I'll do is I'll get an email from you, actually from Bitbucket, that says, you know, this student wants to add you to the repository. I will confirm that add, and then I will check to make sure that your files have been checked in, and if I see those files that are there, I will then mark your assignment as being complete. So if you've been following along, this should take no more than about 10 or 15 minutes to do. You're just taking existing programs you already have and just putting it under version control. The whole point here is just to make sure that you've got an account created, you know how to create a repository, you know how to push files, and then share it with me. That's all it is. So no programming work this week. You can continue to work on your CSI assignment if you're still working on that. Okay, any questions before we go ahead and call it a day? Nothing? Sorry, I had to rush it there at the end a little bit because I have stuff to go do. So, no, I don't hear any questions, and the YouTube folks have grown extremely quiet over the past 10 minutes. Nothing else? Chris, sounds good?
Yep, sounds good.
Yeah.
All right.
So,
well, thank you.
So I guess the last thing is, in my instructions for the assignment, I talk about creating a directory and then copying the files into it. My experience has been, I think I'll probably update the instructions when I get a chance, is to go ahead and open the workspace in that directory. The biggest problem that students have run into is they might accidentally run that git init directory. They might type in git init by itself, and that creates one giant repository for all of your files. And that's not what we want at all. We want one per homework assignment, and that requires one directory per homework assignment and per repository. And so I've had to go into students' workspaces and fix the Git problems. And so I really like the idea of opening a workspace in that directory and ensuring that what you do in that workspace doesn't bleed out and cause problems in other workspaces. So I may go and update the instructions to reflect that. If you create an account with your Gmail, it won't be a premium account, you'll just get a free account. I had contacted the Bitbucket folks and told them, this is the account I'm going to be using for my students. Can you just make sure it's the premium account? And they said, no problem. So that's how I got that set up. But if you're just following along, the free account will be just fine. It allows you to collaborate with up to 5 people, I think, per repository, which is plenty for doing student work. Okay, I think that's it for today. Easy.
Well, thank you.
Yep.
Have a good rest of your day.
So we will talk about the debugger next time. We'll get to it. I mean, we really have to start talking about it because it's going to be imperative for working on these larger programs, particularly when things start crashing all around you. Okay, so we'll do that next time.
All right.
Okay. Have a good weekend.
All right. You too. Bye.
Right. Bye-bye. Okay, well, sorry, YouTube folks, I have to get going, but we covered a lot of ground today, and I hope this was useful for you. To address the last comment that just came in, so we're using, and this is an introduction to version control, right? So we're not doing anything super sophisticated with it. What a real development team would do is not have people checking in and pushing code up to the central repository all the time. What they would do is they would maintain their 2 separate repositories. You got your main one, the shared repository, and then you got your local one on your computer. And no matter which repository it is, you can do something called creating a branch. So you've got like your main line of changes. So a change happens, a change happens, a change happens, a change happens. You can create a branch, which basically forks off a separate line of changes. And let's say you're working on a bug. You need to fix a bug. So you create a branch, and you might call it bug fix, and then maybe a number, which indicates the bug number that you're fixing. So it would be a reference to the bug tracking software that you've got. And then you make your changes on that branch, and it's not causing anything to happen along the main line. So you make your changes along this branch, and then when you're ready, when that bug is fixed, and you have someone go and look at your code and verify that it's fixed, then you can do what's called a merge. And that's where you take the changes that have happened on this branch and merge it back into the main line. But the only thing that merges into the main line is just the finished change, right? It doesn't merge in all the little changes you did on that branch. And so what it allows you to do is keep the main line relatively clean of a whole bunch of versions. The only thing that's being pushed into the main line are just these merges from these other branches that are being created. So there may be hundreds of branches in a project, but only the main line contains the major changes. And in fact, you don't even have to push your branches up to the shared repository. You can keep those branches on your computer, because maybe you're the only person fixing that bug. And then when you're done fixing the bug, you can just delete the branch. And all of your changes, all the record of your changes have gone away. If you do need to collaborate with somebody else on that bug fix, then you would push that branch up to the repository, the shared repository. But again, after the bug was fixed, you could then delete the branch, or you could archive it so it doesn't show up on everyone's branch list, just to indicate that I'm done with this branch for now. Store it away, but don't show it to everybody. And oftentimes you'll appoint one person or a very small group of people who manage that mainline branch, who are responsible for doing those merges in. So you might have individual developers doing changes and branches, work on their own branches, and then one person or a very small group of people is actually responsible for bringing those changes in from those branches into the main line, because they're responsible for keeping that code as clean as possible. All right, so that's a lot of stuff for today. We will talk more about version control as we go through the semester. But right now, we got to call it a day. I'm glad you could all join me, and I will see you next week. Have a good weekend, everyone. Goodbye.